So in the last video, we talked about eigenvectors and eigenvalues. And we did a quick example of how you can use eigenvectors to find eigenvalues. And today I want to talk a little bit more about how to find those eigenvectors and eigenvalues. So going back to our previous definition that we learned, we know that if we have A being a square matrix and we have X being a column vector, and with lambda being a scalar, if we have the equation A times X equals lambda times X, then we know that X is going to be an eigenvector of the matrix A, and lambda is going to be an eigenvalue of matrix A. So what we'll do is we'll continue using this formula to help us figure out what the eigenvalues and eigenvectors of a certain matrix A would be. So we're going to use that same formula, and I'll copy it down over here. So A times X is equal to lambda times X. So if we know that this equation is true, what we can do is we can subtract lambda x from both sides. So I'm going to subtract lambda x on the right side, and I'm going to subtract it on the left side of the equation. Now when I do that, they're going to cancel out on the right side, leaving me with a 0. But on the left side, I'm going to have ax minus lambda x. So now I've got both terms on the left side of the equation together. So now, if you look at the equation, you'll see that both terms share an x. So what we can do is we can factor out the vector x. We can take that out, and when we divide both sides by x, we're left with a minus lambda. But really, we need to make this into a matrix, so we're going to multiply lambda by the identity matrix. So that's where that I comes in. And if you remember, the identity matrix is a square matrix where you have ones down the main diagonal. But in the other places, you'll have zeros as entries. So for example, this would be the 2 by 2 identity matrix. So now that we know that, we need to remember that in this case, we know that the vector x cannot be equal to 0. So vector x can't be the 0 column vector. So what we have to do is we have to assume that x is non-zero, and then what that means is a minus lambda I must be equal to 0. Now, if that's true, then we know that a minus lambda I must be non-invertible. Non-invertible. So what that means is you can't find the inverse of the matrix A minus lambda I. Now, since we know that non-invertible matrices have a determinant of 0, now we can say that the determinant of that matrix must be equal to 0. So the determinant of A minus lambda I is equal to 0. So this is going to help us figure out what the eigenvalues of a matrix are by using the determinant to find that out. So let's go with the example from last time. Let's say that matrix A is equal to 1, 4, 2, 3. Right? This is our square matrix. And what we're going to do is we're going to subtract lambda I. So A minus lambda I. We can write that out. So we know that matrix A is 1, 4, 2, 3. and we're subtracting lambda I. We know that I is 1, 0, 0, 1. That's our identity matrix from up here. And we're going to use that, and we're going to multiply every number in the identity matrix by this lambda right here. So if we do that, we're going to get minus lambda, 0, and 0 lambda. And that's going to give us a new matrix. Once we subtract these two matrices, we'll get 1 minus lambda, 4 minus 0, that would just be 4, 2 minus 0, that would just be 2, and 3 minus lambda, we can write that like this. So this is our new matrix. And now what we want to do is we want to find the determinant of that. So to do that, what we're going to do is we're going to multiply the elements on the main diagonal We'll do that first. So if we do that, we're going to get 1 minus lambda times 3 minus lambda. Those are the elements on my main diagonal right here. And then we have to subtract 2 times 4, the product of the other elements that are not on the main diagonal. And all this must be equal to 0 because of our equation up here. So now we can multiply these two factors together. If we do that, 1 times 3 is going to give me 3. Then 1 times negative lambda is going to give me minus lambda. Negative lambda times 3 is going to give me minus 3 lambda. And then negative lambda times negative lambda will give me a positive lambda squared. And then I have to bring down my minus 8 and set everything equal to 0. So now you'll probably notice that there are some like terms. I can bring down my lambda squared, and then I can combine these two lambda terms to get minus 4 lambda. And I can combine the regular numbers 3 and negative 8 to get minus 5. So now this is looking more and more like a quadratic equation. So now I'm going to try and factor this. So to multiply to negative 5, I'm going to have to use a negative 5 and a positive 1 because those add up to negative 4. So I'll have lambda minus 5 and lambda plus 1 is equal to 0. So now if I solve these two factors being equal to 0, I know that lambda minus 5 has to be 0. So that means lambda has to be a positive 5. So lambda has to be a positive 5, or if you solve this one being equal to 0, you'll get negative 1. So lambda can also be a negative 1. So these are my eigenvalues.